Welcome to Manish Kumar channel. Today we are going to talk about linearly independent vectors. Okay, so what is the definition? A set of vectors, say v1, v2, vn, in a vector space V is said to be linearly independent if if the equation alpha 1 v1 plus alpha 2 v2 and so on alpha and vn, where each alpha i's belongs to the scalar field real number for all I from 1 to and so on n. Okay, then this linear combination is equal to zero vector, right? This is a zero vector. This linear combination goes to zero vector for all scalars, and this is going to be linearly independent if this equation has trivial solution. It means if each alpha I goes to 0, alpha I is equal to 0, right, simultaneously, then we call it as the system is linearly, the given set is linearly independent. Okay, otherwise we call it as dependent. Okay, so it means that there exist scalars, right, not all zero, such that the above equation goes to 0. Okay, so for linearly independent, every alpha i's must be 0. Okay, you can write in a compact notation alpha I vi I run from 1 to n is equal to 0 vector, right? The same above equation. Okay, so let us see the properties of the linear independence. So 0 vector, first property, if v1 v2 vn are, contains the 0 vector, any one of them in this set contains a 0 vector, then they are linearly dependent. Why? You see, I'm going to multiply 0 times of v1, 0 times of v2, and so on, all the combination. Because it consists of 0 vector, this set consists of 0 vector, I can say 0 vector multiplied by non-zero constant, right? Scalar is non-zero, so there are some scalars such that this linear combination goes to still 0, right? So this set is linearly dependent, right, as per the previous definition. Second property, subsets. What is this property? Any subset of a linearly independent set is also a linearly independent, right? Because a smaller set is also going to be linearly independent. Okay, what is the dimension property? If n vectors exist in an m dimensional vector space and n is strictly greater than m, then the vectors are dependent by the rank nullity theorem that we will discuss in next video, right? But for a moment you remember this property. So determinant test, a square matrix A whose column represent the given vectors is linearly independent if determinant is going to be 0. Determinant is going to be 0 means A is single, A is non-singular, right? If A is non-singular means RREF, all the column has non-zero pivot entry, right? It means rank of A is equal to the rank of full rank. A has full rank. A has full rank, right? Okay. So all the vectors are, so none of the column vector can be written as the linear combination of others, right? This is for the determinant test. Next, row reduction test. If all matrices, if all matrix formed by the vectors as column has full rank, right? That means all pivot columns, the vectors are linearly independent. Orthogonality property, a set of orthogonal non-zero vector is always linearly independent because vi dot vj is equal to 0 for all I not equal to j implies independence, right? Means orthogonal vector cannot be written as the linear combination of the other vectors. Okay, Now the method, independent test method. How do we test for a given set of vectors are linearly independent or not? So we will use independent test method where if you remember we have done before the spanning uh, minimum spanning test method. So where we have allocated every vectors as a row element. Now in independent test method every vectors can be allocated as a column of the given matrix A, just reverse of that, okay? And bring the matrix RREF, bring the given matrix into an RREF, that is a row reduced echelon form, and the vectors corresponding to the pivot columns are linearly independent, and remaining vectors are linear combination of them, right? So let us see how to do independent test method. So example. Independent test method for a given set of vector 1 2 3 4 vectors are given, right? So first we can perform the matrix by taking these vector into a column wise, right? So these vector 1 1 0 0 2 3 1 2 3 3 6 6, right? Apply RREF, apply RREF. So you see first row first column element is 1, so I want to get 0 here, so subtract this operation to get this matrix, right? And then again this entry is 2, we want 1, right? So we have to divide R2 by 2, R2 by 1 by 2, right? So what had happened here, you see this operation is used, we got the second matrix. Similarly, I want to make it 0 to the below column, below pivot column, so apply this operation, we get the third matrix. Similarly, I want to make the last pivot as 1. So I've used this operation in the previous matrix. 3 by 2. So we have multiplied 2 by 3 so that it become 1. And then finally we got the final matrix, right? So finally 1 pivot, 2 pivot, 3 pivot. So you see here 3 pivot we got. In that case, the last vector, right? First, second, third contains pivot, right? So first three vectors are linearly independent, while the fourth vectors is a linear combination of them, right? So if you want to make the linearly independent set of these vectors, so you have to actually throw out this vector from the set. So remaining set becomes linearly independent, right? We will see how to find a basis in the next video. So let us do one problem. Suppose you have a set of vectors v1, v2 and so on vn that are given as linearly independent. Now consider a new set of vectors where each vectors except the last one is replaced by the difference between it and the next vector. What does it mean? First vector will be the v1 and difference between the next vector, right? So v1 minus next vector will be the v2. So v1 minus v2 will be the new vector. v2 minus v3 will be the new vector and so on. Construct the set, okay? And except the last one as it is. Now prove that this new set is new set of vectors is also linearly independent, okay? So how do we prove that? So suppose it is given that v1 v2 vn is linearly independent in v, right? So what we have to prove, the new set is linearly independent, okay? Suppose alpha 1 alpha 2 alpha n belongs to R such that the new combination alpha 1 with first vector, alpha 2 with second vector and alpha n minus 1 with nth minus 1 vector and this nth vector, that linear combination goes to 0 vector, okay? Now in the left hand side we are going to rearrange the terms, right? So after rearranging we got this term, right? Okay, and since we already know that this set v1, v2, vn is linearly independent. What does it mean? This is just the linear combination of the new vectors, right? So what it says, the coefficient must goes to 0 simultaneously, right? So alpha 1 equal to 0, and then second one alpha 2 minus alpha 1 equal to 0, and so on, alpha n minus 1 equal to 0. So if you use the first equation, second equation, third equation, and so on, nth equation, if I say, so first equation, if you use first and second, what you will get? Alpha equal to alpha 1 equal to 0. Second, alpha 1 equal to 0. If you plug here, what you'll get? Alpha 2 equal to 0. And when alpha 1, alpha 2 0, you will get alpha 3 0. And so on, alpha n 0 you will get, right? So it means these combinations, alpha 1, alpha 2 minus alpha 1 is 0, right? And from the first equation, we find that alpha 1 is equal to 0. Similarly, the same explanation, right? So what we have concluded that alpha 1 equal to 0, alpha 2 equal to 0, and so on, alpha n is equal to 0, right? So whatever the linear combination you are going to write is going to be 0. Hence, what we can say, this set is going to be a linearly independent, right? So this is a new proof, right? So this is the proof done. Thank you. Thank you very much. Thanks a lot.